Hey everyone, my name is Hui Lu. Today I'm going to present our paper, Composition Sampling for Improved Convergence in Diffusion Models. Nowadays, diffusion models can generate diverse and realistic images. However, when we look into the training details, we can see that diffusion models consist of many time steps, which is generally 1000 in total. This high number makes the training cost of diffusion models very high. A natural thought is to reduce the time steps t to accelerate the training process. But the problem is if we reduce the time steps, at each time step, it will be more difficult for the model to reconstruct the image at last time step. This will reduce the image quality. Our target is to accelerate the training process by reducing t while improving the image quality. To realize this, we first mathematically express the diffusion process as this formula. We further define the denoising process at each time step as this formula. In summary, the diffusion process can be expressed as the blue one. Our target can be defined as the red one. We further define two terms, the composition weight and the initial reconstruction of X0. Our composition sampling process can be defined as following. You can pause here to check the derivation process of the formula. When comparing with previous sampling approach, we can see that previous sampling directly takes xt as input and generates xt-1 through multiple network trainings. This method is not only time-consuming, but also does not guarantee a high-quality xt-1. Different from previous method, our approach model can always reconstruct xt-1 without multiple network trainings, which not only improves the quality of the generation but also speed up the training process. Looking into details of composition term, we can see it actually learns the difference between the current generation X0 hat and original image X0, which means that it actually guides the generation direction towards the original image distribution. This can explain why it can not only have the model convergence, but also improve the image quality. Ideally, we can animate the process as follows. Given the noise data distribution X3, the original sampling approach follows the blue line to generate the images. We can see that this approach has no clear generation direction and will deviate from the clean data distribution. Our approach is the red line, which aims to add composition during each time step. This direction is towards the original data distribution so that it can accelerate the training process while improving the generation quality. We did experiments on popular datasets and reviewed three contributions of our work: faster convergency, better image quality, and application on multiple tasks. By inserting our approach into DDIM, we can see that our approach achieves the convergency at around 2 hours after training, but DDIM at 1000 time step takes around 16 hours to achieve the convergency. Although for DDIM, reducing the total time steps from 1000 to 100 takes only 8 hours, it also reduces the image quality. You can see that the effect score at this condition is much higher than previous. Our approach also has other backbones to get improvement on unconditional generation tasks, and we achieve new SODA results on SURF-A, FFHQ, and CIFAR datasets. Finally, this is the result of our approach on unconditional generation tasks. Except for this, our approach can also be applied on phase imprinting task and phase de-occlusion task. Phase imprinting is to restore missing or damaged parts in phase image, resulting in a complete facial image. It is a conditional image generation task. Compared to phase imprinting, phase de-occlusion is more challenging, since the missing contents of the face images are not black pixels but pixels with values potentially similar to faces.